During the architectural layout process, you're going to be moving things around on your printed circuit board, including the antenna, to optimize where things are inside your device. One thing I'd like to mention is something that's not always taken into consideration, which is the plastic housing that your device is integrated into. If you've chosen the flexible printed circuit antenna, then your antenna is going to be stuck to the inside of that housing, and the material that you've chosen can influence the performance of that antenna. I shouldn't have to mention, but I will, that placing the flexible printed circuit on antenna on a metal housing is going to impact the antenna in such a way where the antenna will more than likely not work. So please avoid all metal housings. If you have to have a robust housing that requires some thickness to it, take that into consideration that thicker chassis or chassis made of glass-filled substances will tend to have a dampening effect on the antenna, and you may have some reduced performance. Embedded antennas work a couple different ways. There are antennas that require a ground clearance area underneath the antenna to operate properly, and there are also surface mount antennas that will work on a ground plane where you don't have to clear the copper layers out underneath the antenna. The difference in performance of these two antennas is that the ground clearance antenna will operate in a more omnidirectional or kind of a donut type radiation pattern, whereas the on-ground antennas, they tend to have a little bit of shadowing caused by the ground plane underneath the antenna. Also, you want to consider the different types of antennas you choose, such as the dipole versus the monopole antennas. Dipole antennas are more balanced and they do not require a ground plane to be attached in such a way where the antenna is reliant on the size of the ground plane, whereas the monopole is going to require that the counterpoise or the other side of that monopole antenna is your ground plane, and it's going to be necessary to design a longer ground plane in order to hit the lower frequencies. Inverted F antennas versus planar inverted F antennas versus magnetic loop antennas all work well next to the body, so using them in wearable devices is typically better than a dipole versus monopole. The difference between an inverted F antenna and a planar inverted F antenna is that the planar inverted F antenna is perpendicular to the ground plane, similar to a blade style antenna. Continuing on the architectural layout, you are currently trying to enhance your electrical performance within the smallest package possible. Something to consider are the carriers that you're looking to certify your device with. Some carriers out there offer small device requirements that are less stringent than the other carriers. One other thing to keep in mind is the stability and reliability of your antenna installation during your manufacturing process. Pick-and-place systems work faster and are set up for higher volume manufacturing than hand-placed antennas such as the FPC antenna. You also want to consider to place your radio near the antenna, which will reduce the length of your antenna feed trace and cut the losses that longer traces with bends in them can cause between your radio and your antenna. You want to try to avoid all loss at all cost. Also, switching power supplies and digital lines, I mentioned this before, should be routed away from the antenna area. Moving to the board design, you want to consider the wireless integration for noise rejection. One of the best ways to route a trace from a radio to your antenna is using a grounded coplanar waveguide antenna feed system. What this does is it uses ground on either side of the feed trace along with ground underneath the trace and vias stitched along connecting the two layers of ground above and below the trace to create a waveguide. And the reason for this is that it improves the impedance. It gives you the ability to tune the impedance using that trace. And it also keeps a lot of the noise from coupling to the trace. So you want to also consider laying out your digital components on a separate digital layer. And anytime a trace has to come up to the surface, you want to apply bypassing capacitors to those traces so that they don't tend to radiate. Choosing a 2-layer, 4-layer, 6-layer, or even an 8-layer board will be beneficial in the choice that you do make. A 2-layer board tends to be broken up by the traces that run up and down the board from one component to another, and they slice through the ground layers, so you end up having a non-contiguous ground plane to offer to the antenna. This will end up having the antenna see an electrically short ground plane due to the breaks in the ground plane. So choosing a 4-layer or even a 6-layer board where you can have a ground layer on the top and bottom of the printed circuit board is beneficial. And the reason why is because it offers a longer contiguous ground plane, not broken up by traces running through it, and allows the antenna to see a magnetically straight ground plane. Following the design guidance for the ground clearance and the keep out areas for the antenna is also very important. These stringent outlines are to help with the tuning of the antenna as well as the isolation from noise and other antennas.